Hello everyone. Hopefully you can hear me. Okay, seems reasonable. Don't have enough glare either, and you can hear me. Can't hear me. Well, too bad. It will be I will align the audio on Anchor. So where the boundary are. Yeah, so here you can see me, and here you can see. Okay, so we got plenty of space. Anyone? There are a few people waiting. Oh well, I'll start anyway. But there are 8 of you. Success. Hopefully it's not random people just joining the live stream, but there we go. Okay, welcome everyone. So as you've seen, we got a little bit of a different lecture format today. So hopefully everything will go smoothly. And it's also our last lecture. So a couple of things before we start talking about noise in MOSFETs. So first things, a few of you asked me if I knew anything about exams, and the answer is no. I know nothing about exams. I have no idea what's going to happen. So the university will let us all know, hopefully soon, what's going to happen, and then we'll take it from there. The other things, I will upload a revision guide similar to what I've done at the end of the first term, so you can check exactly what to revise, what you need to memorize, what you don't have to memorize, what you need to be able to derive, etc., etc., etc. Okay, so this one is hopefully will be helpful for you for your revision. Okay, now moving to today's lecture. Start talking about noise, okay? And specifically, it's going to be noise in MOSFETs. Okay. Now, you've seen already quite a few things about noise last year with Holton, I believe, in sensors and actuator. And in fact, you may have seen something the first year as well when you done your electronics measurements course. And if you're on the MC degree, then some form of another, you should have seen a little bit something about noise. Okay. In any case, let's have a very quick recap of what noise is and what noise means. If we take a circuit, so a very simple circuit, right there, and perhaps a voltage divider, okay? Right. And we got our output there, the out. Doesn't matter the value of this resistor, etc., just as an example. And we plot V out as a function of time. What we have is not a nice continuous continuous signal, but it will be something like this. Okay, we will have a fixed average value and then fluctuation on top of it. Okay. Now the average value here is what we usually refer to the voltage of the node. Okay, so what we refer to the voltage of the node would be the average of the voltage, the time average of the voltage. Okay, but we need to have a way to quantify this fluctuation and to quantify both the behavior as time series as well as the amplitude. Okay. Now, the amplitude is quantified very easily by the RMS value. Okay, so you keep so typically these things is done by keep measuring the voltage as a function of time, and then to see where the RMS value is across the average. Okay, so probably some variation. So this is our RMS value. Now, the behavior of the fluctuation is very well modeled by the power spectral density, the noise power spectral density, okay, which tell us how the fluctuation are distributed in frequency. Now, this is all things you've done already. Well, if you remember, a very common type of fluctuation is white noise, okay? Not the only one, but definitely a very common type of noise, white noise. And in that case, if we plot the power spectral density, which tells us what the amplitude of the fluctuation at different frequency, we have a straight line, okay? Is constant. Okay, this is the which will indicate as the magnitude of V square, okay, the voltage noise. Now, a question then people immediately ask, and you should ask yourself, is, well, but if this one is a constant, okay, the total power then this noise provided to a load is an infinite power, okay? So where does the power comes from? And in reality, this is not a constant line. So as you go to very high frequency, when you get to hundreds of gigahertz, this power spectral density takes off, okay? So the total area there, which will give us the amount of power that the noise can provide to a load, is actually finite, okay? So we don't have any strange behavior. Now, if you remember, so let's go back to our, okay, just to give you an idea, at room temperature, this drop here is approximately 6,000 gigahertz, okay? So for normal operation of circuits, you're fine, so you don't have to worry about this drop. If you go up to 100 gigahertz, though, you need to be careful because this area start drooping, so you need to account for it properly, okay? But the constant approximation, the white noise approximation for any usable frequency in conventional circuits is absolutely fine, okay? So if you remember, so white noise, okay. In a resistor, this white noise spectrum is 4kTr, okay, where K is the Boltzmann constant, T is the temperature in Kelvin, and R is, to have a quick recap from what you've seen in previous year. So we got the power spectral density of the voltage noise is 4 kTr, and of course we can consider the current spectral density, okay, by converting voltage to current using a Thevenin to Norton equivalent as usual. So this one as I with 4 kT over R. Okay. So these two expressions here give us the white noise approximation of the noise spectra for voltage and for current. Okay. Now, if you remember from a previous year, we also have what is called Schottky noise and other type of noise. We won't consider them. We're gonna have a very brief look at the flicker noise toward the end of the lecture, but for the moment we just focus on white thermal noise. Okay. And you see that this one depends on the temperature. Okay, so the lower the temperature, the lower the noise is. Okay, and this is quite important because if you want to have a circuit with very high noise performance, what you do or what you can do is to lower the temperature. Okay, it's very common in application in radio astronomy, for example, where you keep your transistors, your MOSFETs, in liquid helium. Okay, so you go down to 4 Kelvin, for example. So the noise is almost 100 times lower than at room temperature. So that's it's very common common approach. Right, let's see inside what happens in a MOSFET. which is right where your handout starts today. Now, if we take a MOSFET, so if you go back to our MOSFET structure, which by now you should know, should be familiar with, this, let me see, marker pen is here. Hey, that one. Right. So this one here is our bike. Okay, then we got N-type P MOSFET. Sorry, an N-type MOSFET. So we have a P-type substrate. This one is P-type. Then we got our source and drain contacts, gate oxide, and gate contact here on top. Okay, the gate. This is our drain. This is our source. So what we have here is an electron channel, okay? Because we are when the MOSFET operates as a transistor, we will have a channel made of electrons, okay? Because it's an N-type. Okay, so we can think of this channel as a sort of resistor. Okay, it's not quite a resistor because the resistance of the channel changes. Depending on the location. Okay, so what we can do to slice the channel and consider the individual slices as resistors. Okay, consider the individual noise contribution and then add up the contribution. Okay, now we're not going to do that step by step because some of you are not doing semiconductor physics. Okay, so I can do that, but however, this comes from a gradual channel approximation. So if you've done the gradual channel approximation, you can actually try on your own. That would be a very good thing. So, okay, to slice the channel, combine all the contributions together, and see what the final result is. Okay. In any case, so if you do that, we end up with something like this. So this is our MOSFET. And here we have a current source which models our noise. Okay, so this one will be SI, okay, because it's a current, the noise current. Okay, it's not voltage. Right. So our KTGM, you can think of it as 4kT divided by the resistance of the channel, 1/Gm. So the Gm transconductance goes on top. And then there is a coefficient here, gamma. And this coefficient takes in account of the shape, the profile of the channel underneath the gate oxide. Okay. Now, the textbook value of gamma, which comes from the gradual channel approximation, is 2/3. Okay. Now, this 2/3 value is a textbook value. Is not something that is typically found in practice. In practice, can be anything between 0.2, 0.3, and 1 point something. Okay, so gamma there, I say 2/3 is our textbook approximation. In practice, this is something that will need to be measured. Okay, so in your noise model on SPICE, for example, you will have a gamma, and this gamma comes from measurement. So when people design devices, the device get tested, and people extract this parameter, and they put them in the SPICE model. Okay, so this is not something. So 2/3 is just indicative, but it just gives you some decent results. Okay, if you do calculations using 2/3 as a parameter there. Right, okay, so this is our noise current source there. However, very often we want to have something at the input of a transistor because you want to compare the noise source with your signal, okay? Because at the end of the day, what you care about is the signal-to-noise ratio, not the actual value of the signal over the actual value of the noise. You want to compare the two. So to compare the two, you need to either compare the noise at the output of the noise and the input. Okay, and typically you want to compare the noise at the input. That's more common and what you find in data sheets typically. Okay? So if you want to move this current source to the input, so what we do is the voltage source there as V, okay? And to move it before SV and SI, since the current is proportional to the transconductance, so the voltage square, our voltage power, is proportional to 1 over Gm square. So we have then SV. Let's put in the board if I SV equal 4 kT gamma divided by Gm. Okay? So when you multiply by Gm square, you recover the same ball. So you can either use this one or this one. You cannot use them both, obviously, otherwise you can't denoise twice. But you can use the voltage source. The voltage noise at the input as a much better way to describe the performance of this MOSFET in terms of noise, at least, because you can compare directly with your input signal. Okay. Right. Oh, see the numbers here are going up. Right. Right. Okay. So we've seen how we can account for the noise in a MOSFET. Well, what we're going to do with it? Well, the easiest thing is to see how we can use these current sources or voltage sources to build an overall model, noise model of a circuit. Okay. So the circuit we are going to see now, and the only one we are going to see today, is the differential amplifier. Now, why the differential amplifier is not something else? And because the differential amplifier is often the fourth stage in a more complex amplifier or a more complex circuit. For example, if you remember our simple operational amplifiers, we had a differential amplifier followed by a common source amplifier. Okay. Now, typically, when you do a noise analysis, you only care about what's called the first stage. And the reason is that if you have a chain of amplifiers, okay, say two, for example, this one can be our differential amplifier, this one could be our common source amplifier. Say then we got G1 and G2. The gain of the first amplifier, the gain of a second amplifier, and these two amplifiers have the voltage input noise source, call it SB1, that's B2. Now, since we are interested in the noise power, which means everything needs to be squared, if I move this second noise source at the input there, I will have to divide by G1 square, okay? So in this case, we will have G1, G2. This I move it here, and what I have is SB1 and SB2 over G1 square. Now, you see then if the gain of these amplifiers is relatively high, for example, in our the amplifier we've seen typically in the order of 100 to 200. Well, you see then, say then G1 is 100, well, the effect of SB2 is attenuated by a factor of 10,000, okay? So as long as the noise of the first stage is low, or is low enough for your application, then you are usually fine. You don't have to worry too much about the other stages, okay? Now, it's a different story if again then you're using is low. For example, if your first stage is a gain of 2, well, this one then is reduced by a factor of 4. So if you do a good design in the first stage, but then a very bad design in the second stage, well, then it's a problem, okay? So, but as long as you keep the gain relatively high in the first stage, then you're fine. Okay. So that's why we're going to see the differential amplifier, because that's typically the first stage in a more complex amplifier. So it will be the stage which will be responsible for the noise performance of your circuit. Okay. As I say, we could consider other things, but this is perhaps the easiest way of having some results, and then you can actually use in designing things. Okay. Right. So let's see what happens. Our differential amplifier. So I'm going to use the differential amplifier with the active load when put the current mirror on top of the differential pair. Okay. And I'm using, so in your handouts, I've used an N-type differential pair, I think. Yeah. The VDD. So here is current mirror made with P MOSFETs. This is our tail current generator. That is out. Okay. And this will be the non-inverting input. This will be the inverting output. Okay. Actually, let's instead of using a current generator there, we're going to use a MOSFET, because we know already that is built using a MOSFET that typically a current mirror. So let's replace this one the MOSFET, so we can consider the noise of this MOSFET correctly as well. Okay. Right. So step one, you draw the current sources, the noise current sources attached to each MOSFET. Okay. So in this case, we will have draw them in blue. Okay, make it clear. This one is 1. Oh, actually, I got this one as I1. Let's use the same as I2. Got as I3 and as I4. Okay, and then as I5 over here. Right. So now we need to see how these sources here combine to give us an output noise. Okay. So what we want to know is what the effect then we have here at the output. Okay. So the easiest way of doing it is to see, well, how these noise currents add up at the output there. Okay, it's perhaps the easiest way of doing it. So can we replace all these current sources with an equivalent term at the output? Okay, this is fairly straightforward to do, because you see then this source here, I4, I just connected between VDD and the output. Okay, so this one goes straight to the output. Okay, so if I write SI out, okay, got SI4 goes straight to the output here. Okay, got SI4. Then SI2, again, at this node there, the source of the 2 MOSFET doesn't really move. So this is connected directly to the output as well. Cool. Let me see what happens on this side. Well, on this side, we have SI3, which is connected to this node of the current mirror, okay, of these 2 MOSFETs. So if I have a current here, this current will be mirrored, and we end up right on the output, okay? So this is because we have a current mirror. These current sources there get mirrored straight away on the output, okay? So again, we add SI3. And SI1, again, is connected to a point which is fixed in voltage. It's connected to the input of current mirror. The current is mirrored on the output arm, so go straight to the output there. Well, it's actually quite simple, really. Now, as I5, you need to be a little more careful here, because this noise current will split equally between the two sides at the output, okay? So imagine that you got a current flowing down this direction, okay? This will split like this, goes down the mirror like this and get mirror in this way, which cancel out exactly this current here, okay? So these two will cancel out. So we got nothing going out on the output. So the good thing is then I5 does not count for the noise of the amplifier, okay? So you can neglect completely the effect of SI5. Now, pay attention here, because this is only true if you're using an active load, okay, a current mirror. Now, if you were using two resistors here, that would not be the case, because if this current would split, and if you're taking a single end output, then half of this current will be responsible for the noise, okay? So you need to be able to be careful here. However, if you're using an active load, as we've seen in our circuits, then in fact you can neglect I5, okay? So this MOSFET here does not count for the noise. You can actually do that, okay? You don't have to look at it anymore. Right, so we've gone through these, so we found the equivalent current source at the output. Right, how do we convert these current source to a voltage source at the input, okay, which is typically what you find in data sheet. When you get the data sheet, they tell you what the noise of the amplifier is. If you check an operational amplifier, they usually tell you what the equivalent input noise is, 4 nanovolt per square root of hertz, 20 nanovolt per square root of hertz, or whatever, okay? So we need to find a way to convert this current here to a input voltage, okay? And of course, first of all, we need to convert this current to an output voltage, and then we can divide by the gain square of the amplifier, and we find the equivalent input source, okay? So what we want is to find our input SV in, okay? We do not know. That's what we want, okay? Okay, to do that, so we got the current there, so we want to find the voltage at the output of the power of the voltage. So we need to multiply, so typically we will multiply the current by the output resistance there, okay, to find the voltage. So since here we are using power spectral densities, we can multiply by the output resistance square, okay? So we will have then SV out is equal to SI out times R out square, okay? And if you want the input, we need to divide by the gain square, but the gain square is given by the transconductance of the differential pair times the output resistance. So we have then SV in is equal, can you actually see there? Draw it here, yeah. So SV in, which would be equal to SI out times R out square divided by GM1 times R out square. So we got GM1 square, R out square. You see then R out and R out cancels out, and we are left with SI out divided by GM1 square, okay? So we can now put consider every individual contributions there and see what comes out. However, I want to do it as a numerical exercise rather than just write down the equation. So we got an example here on your handouts, and we need to, yeah. And let's see if I can have a little bit more space on the side. Yes. Okay. So first of all, we need to define our parameters. Okay, and we need to define quite a lot of parameters. So we have mu n. So mu n C oxide is equal to 200 micron volt square, mu p oxide 80 micron per volt square. The capacitance of the oxide is 7 femtofarad per square centimeter. Threshold voltage is 0.4 volt for all moment. IQ is equal to 30 micron. Okay. Now, with this parameter, we really need to find all the transconductances of the MOSFETs, okay, and as well as the overdrives. These have been done it 1,000 times by now, so I'm not going to redo it step by step. And we have the transconductance of M1, GM1 is 176 micron per volt, and GM3, which is of course equal to GM4. Okay, the transconductance of these two MOSFETs are the same, and the transconductance of these two MOSFETs are the same. So, otherwise, that didn't work. It's 158 micron per volt. Okay. Okay, now we need to consider all the distributions. Okay, so as we've seen, then our SV in is equal to SI out divided GM1 square. So we need to consider all the Riemann of the four MOSFETs there. So we have 4 KT GM1 times gamma. So this one will be I1. Then SI2 will be exactly the same, okay, because the transconductance of M1 and M2 is the same. So rather than having a 4 here, we can just put 8. Okay, we can move actually 2 times 4. So M3 gamma. Okay, just about. And then all divided by GM1 square. Okay. So here we can simplify the GM1. Here we get the ratio between GM1 and GM3. Here we got AKT gamma, 8KT gamma. So we can simplify and can get 8KT gamma, which multiplies 1 over GM1 plus GM3 over GM1 square. Okay. So if you put the value in, we got 2.7 times 10 to the minus 16 volt square per hertz. Okay. And this one here is the final result. However, yeah, the angle is a bit funny, but yeah. So we got 2.7 times 10 to the minus 16 volt square per hertz. However, if you remember, very often we like to write. I see then got Andrew. Yeah, excellent. Okay. So we got 2.7 times 10 to the minus 16 volt square per hertz. Very often we prefer to use the square root of this value because it gives us a voltage per square root of hertz. Okay. So when we take the square root, so the square root of 16 anywhere. I put it here. Okay, so the square root of SV in equal to 17 nanovolt per square root of Earth. Okay, and this one there is usually what people quote on rather than the square value. However, if you remember, after your coursework on where noise are fit considerably, you should be quite expert on these things. If you remember, the specification were given in nanovolts per square root of Earth. Okay, not in 1 square per Earth. Right, so finally we got our final result, and this one is what goes to worry about all the contributions of the individual MOSFETs. All you care is that is equivalent noise source, and you know how to calculate the value. Okay. Right. Okay. White noise. Any other noise source, and there is only another one. This one is a flicker noise. Okay. So let's stop there. And the flicker noise. Now I really don't want to, because we're going back to this example later. So I change it. Let me push this down and push these up there, which I can't really reach. But never mind. So right. So the other type of noise we're going to see now is a flicker noise. Okay. In previous lecture, but the type of noise that has power spectrum depth, which goes as 1. So it's also called 1 over f noise. Which means if you look at the frequency in log scale, PSD, goes like this. Okay? And this noise does not converge. It does not converge. The noise power does not converge either on the positive side, and it doesn't converge on the negative on the low side. Now, for higher frequency, we don't really have to worry because, like the white noise, there is a drop. Average around a few hertz. What you need to be concerned though is for the low frequency, because this noise does not converge and is never been observed to have a different shape. Okay. Now, in practice, that's not a huge problem because since you get power spectral density 1 over f, it means that you get the same amount of power in a frequency in a decade. Okay, which means the same amount of power between, say, 1. Okay, this amount of power there is the same that you get between 0.1 and 1. Okay, remember the near very log scale on the frequency. Okay, etc., etc. So you quickly go down to a time scale, which would be, comparable to the lifetime of our universe, which a power which is at reasonable values. Okay, so from a practical perspective, there is nothing to worry about. From a theoretical perspective, we say that this is a problem. It's an open problem actually. It's not fully understood. Well, it's not fully understood. It's not understood, and nobody has seen a deviation for the 1 over f behavior. Okay, people has been down. So there is a famous paper where it was an experiment where a set of amplifier was run for a few months. Okay, which give a time frame of at least hundreds of nanoseconds. Okay. In the time scale, and the behavior was a perfect straight line. Okay, 1 over f. Right. In any case, MOSFET do have a fairly high flicker noise compared to other type of transistors, That's why it's important when you account for it, because very often Tisan is the dominant noise in an amplifier. Certainly, it's the case in operational amplifiers. This in CMOS, the dominant noise contribution comes from flicker noise, not from thermal noise. Now, an important parameter is it's called the corner frequency, which is where the thermal noise has the same value as the flicker noise, which means you have a white noise, thermal noise contribution, splatter, flicker noise. This one there is called corner frequency. Okay. So this is an important parameter, is often quoted in the datasheet of amplifiers. Okay. Right, now the model of the noise source is exactly the same as for thermal noise. So we have a MOSFET and we have our current source, noise current source there. One possible expression for power spectral density of flicker noise is this one. Okay, so need to cut the KID. C oxide L square F. Okay, where K is not the Boltzmann constant, but is a constant. Okay. Uppercase. And then we have the capacity of the oxide, the channel length square, and then of course we have the 1/F contribution there. Right, the crucial things here is that this noise is proportional to the current, to the bias current ID. Okay, so flicker noise is a non-equilibrium noise, which means you need to drive a current through a MOSFET to have to observe 1/F noise. Now, it's also quite interesting that it depends on the length of the channel there. And the reason why it depends on the length of the channel is because when you get when you build a MOSFET, the substrate has some kind of defects, and these defects introduce electronic states in the channel, and the rest will be captured and released by these states. And this happens more efficiently close to the pinch-off region. So the shorter the channel is, the higher the field is at the pinch-off region, and this will give you more trapping and release of electrons, will result in a higher bigger noise. Okay, so that's the reason why we got the channel length there. Okay. So I'm done. If you want more details of where this stuff come from, now to work out this one is quite complicated. It's not the only expression for flicker noise. There are quite a few expressions for flicker noise. And you can select different models in your SPICE MOSFET model as well. Okay, so you have to be careful there. You find all this information in a paper, and I put the reference in your handout. So if you want to read about these things, you find more information there. Okay. For what we are concerned, we are only concerned about the fact that it depends on the current of the bias current, and it depends on the oxide thickness and the channel length. Okay. Now we can treat these this problem exactly as we've done with the thermal noise. Okay, so if you go back, these noise sources are now flicker noise sources, and again, the noise of the tail MOSFET here does not count. Okay. Because again, flicker or otherwise splits equally between the two sides, and then it cancels out up the output. Okay? Right, so if we put some number in, now we need to have the constant k, okay? And the constant k depends on the type of MOSFET, is it a p-type or n-type, and usually, normally in silicon MOSFET, the constant for the p-type MOSFET is considerably lower than the one for the n-type MOSFET. So we have 10 to the minus 28 amps per farad, and Kn is 5, 10 to the minus 27 amps farad. Okay. The reason why this happened still not fully understood, but and in fact, if you remember, the operational amplifier with SIN, we use a p-type MOSFETs for the differential pair. Okay, this does have some benefit in terms of flicker noise because the coefficient here is lower. Okay, so we can do it out 1 over f is equal to Si1 1 over f plus Si2 1 over f plus S1 over f plus S1 over I4 over f. Okay, and so we will have 2 times k. 2 times Kn, so let's consider the differential pair first. ID, but ID will be our take current divided by 2, okay? IQ divided by 2. 1 over C oxide, L square, well, 1 square, GM 1 square F, okay? So this only accounts for the flicker noise of these 2 MOSFETs there. And then we have space there, okay, 2k IQ divided by 2 because the mirror has the same current, okay, 1 over C oxide L3 square GM. Oh, no, apologies, it's not the N, yeah, yet. It's going to be too fast. Okay. So this one there is the spectral density at the output of the amplifier. Now, if you want again work out a voltage spectral density, voltage noise spectral density at the input of the amplifier, again we need to divide all this expression here by GM1 square. Okay, so what we can write is S1 SP in is equal to this stuff there divided by GM1 square. Okay, 1 square there, 1 square here. Okay. Okay, now we put the values in. So we got our constant there, our case, we got our IQ, our drain current, so IQ divided by 2, which is our get current. We know what the excited capacitance is, we know what the channel length is. No, we don't know what the channel length is yet. Because I didn't put it there. Oh, actually, it's on your handouts. And is 1 micron. So L1 and is equal, yeah, it's both for both p types and n type MOSFET is 1 micron. Okay. For all MOSFETs. So in this case, we find that then S1 yeah, is equal to here is equal to 7 times 10 to the minus 9 volt square per Hertz divided by f by the frequency. Okay. So this one here is the spectral density of the flicker noise. Okay, the input spectral density of the flicker noise. Now, for the if you want to find the corner frequency, what we do is to put these the flicker noise power spectral density equal to the thermal noise spectral density, and what we get if you do that again, you find the details. The corner frequency equal to 2.6 megahertz. Okay. Now, this is quite an important result, and it's fairly typical in most years, because if you think about building an operational amplifier using CMOS technology, and you're operating with signal in the order of tens of kilohertz or hundreds of kilohertz, you see then really the dominant contribution is really the flicker noise, not the. If you have amplifiers that operate at higher frequencies, then it's a different story, and the noise contribution may. However, certainly at low frequency, the dominant contribution is flicker noise. Okay, and this one is a bit of a problem because CMOS operational amplifiers, for this reason, have a considerably higher noise than other types of technology. For example, if you use a power technology, the noise is considerably lower. Likewise, you can combine CMOS, what's called a bi-CMOS technology, and again, in that case, you can exploit the behavior of the bipolar transistor, the low noise of the bipolar transistors to get a considerably lower corner frequency. Okay. Now, datasheets vary on how they reported these things. Okay, sometimes they state the corner frequency, sometimes they state the actual spectrum, sometimes they state the RMS value of your noise in a frequency band. So they say between 1 Hz and 100 Hz, the RMS value of your noise is, I don't know, that you need to be able to be careful on how these things are accounted for. Okay. In any case, well, we posted on noise just to see if you understood how to use these simple models there, and you actually can go a fairly long way with these simple models. And if you ever have to do design when you need to account for these things properly, I strongly suggest you not to rely on SPICE, but to do it by hand first. And you will actually get a very, very good result just by doing this calculation by hand, with advantage in understand exactly where the noise source, the dominant noise sources are, and so you can do something about it. Right, that's all for today. And again, I remind you then I will upload the revision guide with the lectures on Duo, not only the first term. Please have a look at it because it goes every single part and tells you exactly which equations you have to know. You have to remember which one you need to run, etc. Okay, so it probably won't be today because I'm doing other things, but certainly by the end of the week. Okay. Right, thanks everyone, and let's end the stream.